My invisible friends, hello and welcome back to another video on electrical engineering. Tonight we introduce a new electronic device, the Zener Diode. This is a very special type of diode. We use it backwards. It's called the Zener Diode. We do not use it to rectify currents or voltages. We use it to make constant a certain voltage at a load. The current flows from cathode to anode backwards. The cathode is higher than the anode backwards. Yes, we use it backwards with respect to a rectifying diode. If we use the diode's convention for positive current and voltage, we would have to say that the current in the new device is negative and so is its voltage. But we will not use it to rectify voltages or currents. We use it to keep a voltage constant. Let's take a resistor like the one in the figure and we put a current through it. A voltage drop appears according to Ohm's law. Graphically, that drop produced by the current is linearly proportional to that according to the resistance of the resistor. In a diode, the real diode, when we apply a current through the diode, a voltage drop appears according to that exponential relationship that we have seen, the Shockley's formula. Let me swap the axes ID and VD like so to emphasize the actual nature of the dependence of the drop in the diode to the current in the diode. I was saying, in the diode, we apply a current and that produces a voltage drop. And that relationship was given by Shockley like that. The current in the diode, the regular rectifying diode, that is, depends on the drop in the diode exponentially like this. If we solve for the drop in the diode, we get a logarithmic dependence of the drop in the diode, this one, and the current in the diode. Graphically, it looks like that. That graphic suggests something very interesting, that if we keep the current in the diode between this minimum value to avoid this curve down here and this maximum current to prevent us from damaging the diode, the drop in the diode is approximately constant and it is 0.7 volts. Let me repeat myself. If in the rectifying diode we keep the current between this minimum current and that maximum current, the drop in the diode is constant and is 0.7 volts. How do we use that? Look, suppose that we want to apply a voltage, a DC voltage to the load on the right. We're using a full wave rectifier and a smoothing capacitor. We know that the voltage in the capacitor will not be constant. We'll reach a peak value and then it will drop to peak value minus the ripple. Let's see how we can improve that changing of voltage. The voltage we want in this experiment is 2.8 volts at the load. Allow me to connect 4 regular rectifying diodes in series like that in parallel with the load. If we maintain the current through those diodes between the minimum and the maximum that we saw in the previous slide, the drop in each diode is 0.7 volts and the total drop of that totem of diodes will be 2.8 and 2.8 will be the voltage and the load. This is wonderful, but there is a catch. This works. It maintains the voltage of the load at 2.8 volts as long as the current flowing through the diodes is kept between the minimum current and the maximum current specified. If we go with that current below the minimum one, the drop in the diodes will not be 0.7 and the voltage and the load will not be 2.8. If we exceed the maximum current specified for the design, we may end damaging the diodes. Let's do this numerical exercise, tutorial time. I am not drawing the full wave rectifier on the left of the capacitor, but we all know it is there. We are told the voltage in the capacitor is changing between a peak value of 7 volts and with a ripple of 2 volts. That is, the voltage here at the capacitor varies between 5 and 7 volts. Right. The current in the diodes must be kept, we are told from the data sheet, between 1 milliamp, below which we approach the elbow of the curve and the drop is not 0.7 in each one of them, etc. And below 100 milliamps, which is the maximum current above which we may damage the diodes. That's what we need to do. The load is not constant either. The load is changing between 300 ohms and 1000 ohms. You say, how is it possible? A variable resistor? Not really. That resistor is representing an electric load. Let's say that we're perhaps a smartphone. If you're running a video game on the smartphone will drain a lot of current from the batteries, in this case from the power supply. And because the voltage is constant, it will look like a small resistor. But when you're using no applications, the smartphone is still draining a little current, very little. The voltage is the same. The smartphone looks like a big resistor. That is what that variation in the resistance of the load is really representing. The changes in the duty cycle of that load. That's what it is. Find what should be the value of the limiting resistor. That is the question here. What is the limit resistance if the current in the diodes is maximum? Let's do this. The current is maximum in the diodes when the voltage in the capacitor is maximum 7 volts and when the current of the load is minimal. That is when the load is 1000 ohm resistor. In this circuit, the voltage is 7 volts at the capacitor. The load is 1 kilo ohms. We know the voltage is 2.8 here. We're assuming that the current here is between I min and I max. We need to find our limit. Let's write a k-scale equation of the node at the top. Current entering that node from the left. 7 minus 2.8 divided by the unknown limiting resistance. That is equal to the current through the diodes that we are assuming is the maximum current, 0.1 amperes, 100 milliamps, plus the current in the load, 2.8 divided by 1000. From there we solve the resistance. We say if we lower the limiting resistance below 41 ohms, the current in the diodes will exceed 100 milliamps and bad things will happen. So keep the limiting resistance about 41 ohms. Noted. What is the limit resistance value if the current in the diode is a minimal one? Let's see. The current is minimum in the diodes when the voltage in the capacitor is minimal, 5 volts, and when the load is absorbing maximum current. That is when it is 300 ohms. This is the scenario. 5 volts at the capacitor, 300 ohms at the load. Still we have 2.8 volts at the load in the totem of diodes here. Write a k-scale equation at the node at the top. 5 minus 2.8 divided by the limiting resistance. That should be equal to the current in the diodes that we are assuming to be the minimal current, 1 milliamp, plus the current in the load, 2.8 divided by 300 ohms. From there we say, if we exceed the limiting resistor within the value of 212 ohms, the current in the diodes will drop below 1 milliamp and the voltage clamp will not be guaranteed anymore. Summarizing, the limiting resistor should be between 41 and 212 ohms. For the sake of the argument, let's say that I choose a limiting resistor of about 100 ohms. And then I ask of you, what is the maximum current in the diodes in milliamps? In these conditions, the voltage in the capacitor is changing between 5 and 7 ohms and the load between 300 and 1000 ohms. Same as before, but the limiting resistor is 100 ohms. What is the maximum current in the diodes? Freeze the video, and when you're ready, let it run and look at the solution. Here's the solution, 39.2 milliamperes. That is the maximum current in the diodes. The second question here is, if you choose a 100 ohm limiting resistor, same as before, what is the minimum current in the diode? Well, that happens when this voltage is 5 and this current is and this resistor is 1000 ohms. We solve that KCL equation and get that the current is 12 and 2/3 of a milliamp. The third question is asking us what is the maximum power dissipated by each one of the 4 diodes in that circuit. That's not complicated. We multiply the maximum current that we computed before times 0.7, and that is the maximum power, 27.44 milliwatts. This technique can work and has worked and has been used. The catch is that we have to use a significant number of rectifying diodes to achieve what we want, to keep the voltage and the load constant. It would be better if we could have a single device that does the same thing. Bell's laboratory, using the research of Professor Melvin Zener, Bell's laboratory designed a new device. It called that the Zener Diode to honor Professor Zener. It's designed to operate backwards, and even though it's called a diode, we never use it as a rectifying diode. We use it backwards just to keep a voltage between its terminals constant, as long as we keep the current through the Zener diode between the minimum and the maximum current. We rename the breakdown voltage of the Zener voltage. That is where we will operate. I repeat, it is used backwards. The current through the Zener flows from the cathode to the anode, and we maintain the cathode higher in volts than the anode. How we represent the Zener diode for computations? Let's look at the behavioral curve of the Zener diode. Here on the front, the Zener is just a regular rectifying diode that when the current is between a certain value and another one, the drop in it is approximately 0.7 volts. We will not use the Zener there. We are interested in the Zener, working it in the breakdown zone that we are calling now the Zener zone. In this zone, in that zone, you see that that line's almost vertical. That means that as long as we keep the current between a certain minimum negative value here and a maximum negative value here, the drop in that Zener diode will be constant. That's the device that we want. And the value of this breakdown voltage slash Zener voltage can be specified. We purchase a Zener diode that is good for 5.1 volts, for 7 volts, etc. We specify the Zener voltage. They used to be the breakdown voltage. A regular diode, I insist, and the Zener diode zone, that zone of operation, the third quadrant, because we will be operating on the third quadrant. Let me rotate this diagram so that the third quadrant becomes the first one. That's where we will operate, right? Like this. That's where we will operate. Excellent. Now, instead of using, for instance, 4 rectifying diodes in series to achieve a voltage of 2.8 volts, now we specify a Zener diode connected between the same 2 points backwards, like so. That would be a 2.8 volt Zener. Before proceeding, let's label the axis we're going to be working on. Formerly, This one down here used to be the positive direction for the currents in the rectifying diode. We will not be there. And this one on the left used to be the positive voltage drops in the rectifying diode. We will not be there either. We have relabeled those two axes as the positive Zener voltage on the right and the positive Zener current on the top. We want to represent that Zener diode with an equivalent circuit, one that is made up of ideal components. Why? So that we can use standard circuit analysis methods to solve a circuit that has a Zener diode in it. Let's proceed. The manufacturer will give us the coordinates of a test point here in this region of operation, somewhere there, near the center perhaps, a little bit below that one. That gives us the two coordinates of that point, the test voltage and the test current of that point, VZT and IZT. They also give us the slope of the tangent to that quasi-vertical line at the test point, or rather they give us the inverse of that, 1 over RZT. What they give us is RZT. We know that as long as the current does not exceed a maximum IZM that is given by the manufacturer and does not go below a 10% of the test current, we should be alright. We should be operating in the active Zener zone, and we can represent the Zener as we shall see. In what follows, I will exaggerate the deviation of this quasi-vertical line from the vertical, so that I can see better what is happening in the representation of the Zener, like this. I have exaggerated the deviation from the vertical of that characteristic. I was saying that the manufacturer gives us at a test point what are the coordinates, the test current, IZT, and the test voltage, IVT. They also give us the slope, or rather they give us the inverse of the slope, RZT. We will extend the tangent through the test point until it intersects the horizontal axis at a point Vx. The active Zener diode can be represented by a voltage source with the value Vx, this value, in series with a resistor RZT. That is easy to demonstrate. What is the value of that Vx, you ask? Well, let's write a little equation here. The slope, this slope, is rise over run. The rise is IZT, the run is VZT minus Vx. My equation, the slope 1 over Rz, is the rise IZT divided by the run VZT minus Vx. Solve for Vx, and look, Vx is VZT minus the product of RZT and the test current. That is the formula we will keep in mind, how to find the equivalent voltage source in the Zener operating in its active region. The Zener specs. The manufacturer will give us the Zener voltage that actually we specified when we purchased the Zener. The maximum power the Zener can take, what is the test current at the test voltage, the minimum Zener current at the knee value, the dynamic resistance at the knee region, right below the minimum current, and the dynamic resistance at the test point. We will use the Zener voltage, the maximum power, the test current, and the dynamic resistance. We will not use this one or that one. Let's concentrate on the values we use. How do we represent the Zener diode then? We have seen that, right? We use VZT and IZT, and we use RZT. The inverse of the slope of the tangent at the test point. Immediately with that, we find the tangent to the curve at the test point intersects that with the horizontal axis at Vx, and Vx is VZT minus RZ IZT. And we know that as long as the current in the Zener does not go below 10% of the test current or above the maximum current IZM specified by the manufacturer, this will be true, that the drop is Vx plus RZ IZ. The Zener is represented in its active zone By an ideal diode, it guarantees that the current is flowing from cathode to anode, and as long as that is not, the drop in the Zener is a constant value Vx plus a drop that is proportional to the current through the Zener. Sometimes, when we want an approximate solution to the circuit, we simplify the solution and say, let me assume that this line here is perfectly vertical. In that case, the slope is infinity, Rz is 0, and this model becomes the simplified one on the right. This is the more accurate one, the RV model, and the one on the right is the approximate one, the V model. Let's use the Zener diode. We use it to clamp a voltage, to fix it. Let's say we have a 1N5236B that has a test voltage of 5.1 volts, a test current of 20 milliamps, and the resistance RZT of 17 ohms. This value we will not use, that is the current that they need. The maximum power, 500 milliwatts, will give us what is the maximum current that we can pass through the Zener. There is the original circuit. We have a battery there with a voltage that oscillates. Sometimes it's 12, sometimes it's 14, depending on external factors. And we have a load that varies its value between 330 and 1000 ohms. Between them, I will include a Zener diode like so. Observe the polarity, and to limit the current in the Zener, we have a limiting resistor of 100 ohms. Let's solve that circuit. We are operating in this region here. We know that this test point's value is 5.1 volts and 20 milliamps. Those are the coordinates of the test point. We cannot go below 10% of the test current, 2 milliamps, or above the maximum current, that would be 500 milliwatts divided by 5.1 volts. That is approximately 100 milliamps. The slope is 1/17. We compute Vx immediately. Let me label the top node as Vz, the voltage in the Zener. And the one at the bottom is the reference node, of course. Let's concentrate on what is the current in the Zener for now. That current in the Zener depends on the current in the source and the current of the load, and KCL, of course. Let's see. The current in the Zener is the current in the source minus the current in the load. What those curves? Well, this is the current in the source that is given by Ohm's law. V source minus Vz over 100 ohms. And the current in the load, this one that is given also by Ohm's law, is Vz over RL. The current in the load is Vz over RL. We notice that when we decrease the current in the source and we increase the current in the load, the current in the Zener is reduced. So what is the worst that could happen in terms of the minimum current? Well, that the voltage in the source is 12 volts and that the load is absorbing maximum current. The load would be a 330 ohm resistor. That is the worst that could happen, that the voltage of the source is 12 and that the load is 330 ohm resistor. Let's replace the Zener with its equivalent circuit, 17 ohms and Vx. The first thing I do is compute what is Vx. 4.76 volts down here. And now we are ready to solve that circuit using M&A, branch currents, and a KCL equation. We solve for Vz, 5.567 volts. And with that voltage, we can compute the current in the Zener. That is this one. That is the current in the Zener. That turns out to be 47.5 milliamperes. That is well above the minimum 2 milliamps currents that we set as a goal. Now, what is the maximum current through the Zener? Well, for that, the voltage of the battery would be the maximum 114 volts, and the current absorbed by the load would be the minimum, so its value would be 1000 ohms. We write a KCL equation, we solve for Vz, 6.015 volts. With that, we compute the current in the Zener, which is 74 milliamps. That is well below the maximum of 100 milliamps, and we are fine. But observe what is the variation of voltage at the load. The voltage at the load is not constant. It is changing between 5.567 volts and 6.015 volts. The voltage at the load has a variation, or a ripple if you wish, of 8%. We have reduced that to less than half what it used to be between 12 and 14. But still, that is not good enough. Let's increase the value of that resistor that limits the current in the diode to see if we can get a smaller ripple at the load. 300 ohms. And we do exactly the same operations as before. We get the voltage oscillates now between 4.9 and 5.2 volts. The ripple is only 5.3%, which is very decent if you ask me. And the current in the Zener will vary from a minimum of 8.8 and a maximum of 24.5 volts. I'm going above, all right? That is well within the limits that we impose to the current. And that is the end, my students. Thank you very much for watching, and I hope to meet with you all again in our next video.